The first stage in dealing with quantitative data is creating a set of summary statistics. So you need to be able to use summary statistics to describe the location and spread of your set of data. What you don't want to be doing is giving the entire set of data. You don't want to be sitting there and writing a report saying, I collected all of this data, and just listing it as a big long list of numbers. You need to find a way of taking that complete set of data and reducing it down to something useful that you can present as a summary within your scientific paper. Now, you're already familiar with some of these summary statistics, so you're familiar with averages such as the mean, median and mode. And averages are an example of what we call a measure of the central tendency. They say, where can I find my data along the number line? If data follows a distribution, and particularly if it's normally distributed, then that's going to be the middle of that distribution. Now, the mode, the least common of these particular averages, is the category with the highest frequency. Now, you can have more than one mode. Ideally, data wants to be unimodal, only have one category which has the highest frequency. Sometimes you get an artificial effect of your histogram that you might end up with a couple of modes, but you don't want two clearly distinct peaks, humps in your data. That's called bimodal data, and it usually reflects you've got a mixture of two different groups within your set of data. That's a problem. The median is the middle value of a set of ranked data. Now, you calculate this by putting everything in a row, order from smallest to largest or largest to smallest, doesn't matter. If there's an odd number of values, you pick the value that's in the middle. If there's an even number of points, you pick the two that are in the middle, and you go midway between those two. Doesn't matter about the distribution of the rest, how close they are together. You just halve the difference between those two middle values. Now, the median is underused. Probably we should use it more often because it's more robust than the mean. By more robust, I mean it's less affected by outliers and bad data. And we'll have some examples of bad data and outliers in a minute. So here, as an example, using class median height. So the median height works out to be 1.67 meters when I use all of the data that I happen to have available. Last year it was 1.69 meters, 1.65 meters this year. If I want to calculate it using Excel, I can use the Excel formula equals median and then pick the heights that I need to use, the column with the heights data. Now, if I categorize the data by gender, I can find out that the female median height is 1.64 meters and male median height is 1.76 meters. This tells you that there's a difference in height between men and women. Now, the calculation of the mean depends on the shape of the distribution of your data. You have been used to just calculating the mean without any kind of thought about what the data looks like, but this isn't actually true. You can only use the formula for the mean that you are used to if your data is approximately normally distributed. So that's the bell-shaped curve. Now, the mean should be represented by x bar. So x bar is what's called the sample mean. So it's an x with a line over the top. When you see the mu symbol, the Greek symbol, that is a parameter, and that's called a population mean. But when you collect a set of data, unless you collected it for everything that exists within that population, it's a sample. So sample mean x bar equals the sum of all of the members of the sample you collected, or the numbers you've got, divided by n. Now, mean, median and mode, that tells you on the number line where the distribution is. But the other thing you want to know is how widely is it distributed along that line? What's the spread of it? How wide across is that shape of distribution, the normal? So what we can use are three different measures. We can use the range, we can use quartiles or sometimes percentiles if you want to have more of them, and we can use the variance. Now, the range is the limits of the data, it includes the maximum and the minimum. This is extremely sensitive to outliers. This is where you're going to get your bad data. Numbers that are too small or too big. They're really going to affect your range. Now the quartiles are much more robust. So the first quartile is 25% of the data will be below it. The second quartile, another 25%, so 50% of the data will be below it. The third quartile, another 25% or 75% of the data is below it, and 25% of the data is above. And the fourth quartile is the maximum, so it's all the data is below. Now a good measure is the interquartile range. So this contains the middle 50% of your data, which should be the best quality data that you've got. If you get rid of the 25% that's at the bottom end and the 25% at the top end, which might contain bad cases. So what you're looking at in the interquartile range is the distance between the first and the third quartile. So how you can summarize your data is something called a 5-figure summary. This includes the minimum, the first quartile, the median, the third quartile, the maximum. This gives you a summary of the range, the median, and the interquartile range. Now this is the 5-figure summary for a set of height data that I happen to have. So it's got a minimum of 1.27 meters, which I don't believe. I think that's an outlier. It's got a first quartile of 1.60 meters, which seems reasonable. A median of 1.67 meters, reasonable. A third quartile of 1.74 meters, reasonable. So the good data is between 1.6 and 1.74 meters. It's got a maximum of 2.8 meters, which I know for sure is an outlier and wrong. This is a wrong piece of data, but it's included in the data set and it is difficult to remove. The good thing about this data is the interquartile range is 14 centimeters in the middle, and that's a very small proportion of the range, which is over a meter. The other good thing is the distance from the first quartile to the median is 7 centimeters. From the median to the third quartile is 7 centimeters. So it is symmetrical between the first quartile and the median, and the third quartile and the median, which is good evidence, though not absolute proof, that the data is likely to be normally distributed. Another measure you can use is the variance. Sometimes you'll have heard people talk about the standard deviation. Standard deviation and the variance. The standard deviation is the square root of the variance. Now I will use both of these sort of interchangeably. The reason for describing the variance is because the way this is calculated depends on the square of things, and it's best if you report it without then taking the square root, because square roots have positive and negative versions of themselves. But I suppose that's a rather arbitrary and excessively mathematical reason. The reason why people don't like reporting variances is because their units are the square of the units that you measured. So if you measured height, the variance is in meters squared, which makes you think, oh, that's area, what's this? Which is sensible because it's the kind of area under the distribution. The standard deviation has exactly the same units as you measured, so its units are in meters. The variance, which is usually called S squared, not sigma, because again, this is a sample variance, not a population variance. So S squared equals the sum of the differences between each of your data points minus the mean of that data set squared divided by n minus 1. Sometimes you'll have seen this formula divided by n. When it's divided by n, that is the population variance, would be represented by sigma squared, and only applies if you've collected every single thing that exists in the complete population. If you have a sample, then you're calculating S squared and you divide by n minus 1 and not n. That makes this number, because you're dividing by a smaller number, slightly larger. So it's called an unbiased estimator of the variance. So to recap, there's a difference between populations and samples. So populations are described by parameters and use the Greek letters, so mu and sigma squared and sigma, whereas samples are described by statistics. That's where the word statistics comes from, and they're represented by x bar, s squared and s.